course will be on dimension reduction, class 17. It is the final of the 4 quadrants of machine learning, which you are now all familiar with, with the supervised, unsupervised, categorical, and continuous. Dimension reduction will kind of fill in that last hole of machine learning that we've yet to talk about. We will talk about the math behind dimension reduction, the code behind dimension reduction, why you should use it, when you should use it, when you should not use it. But before I do that, I actually want to get into a little side project that I put into the fun folder. So a lot of people ask me about jobs, right? Data science, jobs. What's it like to work at Twitter? What's it like to work at Facebook? What's it like to work at a startup? What's it like to be a data scientist in general? I get a lot of these questions, and it's not just at General Assembly I get these questions. I also teach at some other online resources, and this is a common universal question across all students of data. What is it like when I go into my first day of my job as a data scientist? What am I going to be doing? Before I get into my spiel, does somebody like to share maybe an experience that they've had working in a data science, data analytics related role? What is it like? What is a day-to-day data scientist life like? What do you think? I know some of you work in a very, very related field. So what do you guys think? What's it like to work in a data-heavy field?
Yeah. You spend a lot of time trying to find features that are important.
Trying to find features that are important. Okay.
So you have large troves and troves of data, and not all of it is actually meaningful, and not all of it is relevant to what you're looking for. So there's a lot of it that's kind of art, how to transform things, and how to extract things, and how to find things, and how to use your intuition and judgment to uncover what's actually meaningful.
It's a lot of needle in the haystack. Is that kind of what it sounds like?
Yeah.
So you're talking about how you're given a bunch of data, and not all of it is necessarily relevant to the thing that you're thinking about. So maybe you want to kind of extract or select some of the features that are very relevant to you. And today's class focuses heavily on that specific nature. But I think you all are now realizing, as you're going on with your projects, that what makes your models better isn't necessarily a better algorithm. It's usually better data. And better data doesn't necessarily mean more or less, but better data refers to the idea that you're using data, you're kind of narrowing down on the select features of the data that actually matter to your problem. Anyone else? What else? Can someone give me one more person to me? What do you think it's like? A day-to-day life as a data scientist. What is it like? Yeah, that's right.
Let's say that you have somebody in your management chain that says, I want you to answer this question that I have about your area of work. And so, he or she might not understand what is at the root of the question they're asking. They have a curiosity about some aspect that you're responsible for. And you have to distill that broad business question into one that can be answered with data.
That's a very good point. So a lot of the times that we are, a boss that comes into our office, or someone comes into our office, because we have an office and it's awesome. There's jellyfish and a shark in the corner. It's a great office. Someone comes in though, and they have a question. They say, hey, Sanan, what do you think will happen a week after Airbnb's IPO? What do you think is going to happen to the price? Or, hey, Sanan, what do you think is going to happen with what's called? Or what do you think is going to happen with something? Or, hey, I have this data guy just gave me a bunch of data. Can you think you can help me parse through it? I think a lot of it's going to help us identify how to model a user's behavior on Twitter. I'm not exactly sure how, but I think it's there. So people will come in with these very broad ideas or questions about things that they might want to know about. And it's up to the data scientist's job to, A, go through those troves of data and figure out those meaningful nuggets, those meaningful needles in the haystack. And B, as you're pointing out, we have to be able to really quantify the question. Okay, it sounds like the question is, based on such and such and so predictors, can we predict blank with a 75+% accuracy? Fine, let's try that. So it's about how can we quantify and make very precise the question that we're trying to answer. All of you now have experience in this field because all of you started with this very general idea of, I want to try to predict stock prices. I want to try to predict weather. I want to try to predict Uber search pricing. You start with this general idea, and you've been able to hammer it down to, okay, the question I am currently answering is, can I predict if the Uber search price will be above blank percent in a certain time frame, true or false? So you all have experience now with taking this general fuzzy idea and hammering it down into a very precise quantitative question. And at least one question you've done in this class. So the reason I bring this all up is because, well, we can go ahead and talk about it, hold hands in kumbaya and talk about data science all day long, but really when it comes down to it, who is hiring these companies, right? They're the ones hiring the data science position. I wonder what they have to say about it. So I went ahead and made this 27-line script. Well, it's less than that if you take out all the spaces. What the script does is actually quite simple. What it's going to do is it's going to go through, and if you've never heard, has anyone heard of this, the site Indeed? What does Indeed do? Jobs. I mean, yeah, pretty much. Indeed does jobs. You can either search for job postings or you can search for resumes to fill a job. It's kind of like Monster. Monster met LinkedIn. They kind of hung around a lot, and then 9 months later, Indeed was born. So Indeed, essentially, you type in, I want a data scientist position in San Francisco, and you'll get us, senior data scientist at Castled Health, or at Walmart e-commerce, or at Skyrocket Ventures, or at Fitbit. Anyways, sorry. You'll get all of these job listings, right? And you'll read some of the descriptions. Health data experience is a plus, not necessary. Staff data science is a subject matter. Blah, blah, blah. Supervised and unsupervised machine learning, predictive analysis, data mining, visualizations. There's so much crap going on. So I wonder what could happen if we could look at like 1,500 job descriptions at once. That's exactly what the script does. What this script does is it goes through the first 100 pages of this, as if you typed in data scientist and then went through 100 pages of this. I scraped all of the job postings and the descriptions. And then what I did was I used a count vectorizer with an n-gram 1 to 3, and I fit it with stop words equals English. Can someone tell me? Well, actually, let me show you. I went ahead and ran this already because it takes time to go through about a minute. If you want to run it yourself, please feel free. It only takes about a minute to go through the first 100 pages of Indeed. Which actually gives you 1,438 job descriptions. Here's the first one. Expertise in machine learning, statistical analysis, and neural networks, and experience with data mining or remote sensing data preferred, yada, yada, yada. That's the first one of 1,438 job descriptions. So can someone tell me what happens when I create this vectorizer and I fit it to the text? What did I just do? I took a count vectorizer with n-gram range 1 to 3, and I fit it to my text. What did I just do? Think back to the natural language processing day. What does the count vectorizer do?
You just find the most unique words in the descriptions, machine learning.
You're on the right track. Why did you say the word unique specifically? Why did you say that word? Because I know what you're thinking of. You're thinking of the TF-IDF vectorizer, which is a little bit more advanced than what I'm doing, obviously. So I'm not even going into the most unique. What am I doing that's even more basic?
Most frequent.
I'm just counting. I'm literally just counting the frequency of 1, 2, and 3 word phrases. How many do you think there are? In 1,438 job descriptions, and here's one sample job description, how many unique 1, 2, and 3 word phrases do you think there are? About. Give me a guess. 1,000? Hopefully, there's 1,438 just paragraphs altogether. Hopefully, there's more than 1,000 words, 2 and 3 word phrases. 10,000? Maybe. 28,503 unique 1, 2, and 3 word phrases. Which doesn't sound like much, but considering I'm only looking at 1,400 job postings, that's not a lot of jobs. 1,400 job postings is not a lot of job postings, and in them there's 28,000 unique 1, 2, 3 word phrases. And then what I went ahead is I sorted them based on frequency, and then here's what I got. Sorting, sorting, sorting. Frequency, phrase, times, go. Go, go, go. You can do it. This took 2 seconds earlier, man. Classic live demos. I believe in you. Well, there we go. There we go. Let's go ahead and go down this list. I'm going to zoom in. Number 1 word, machine. Fair enough. Number 2, learning. All right. Number 3, experience. All right. The third most used word is not a data science word, it's experience. Because what do most jobs require? Experience. What does General Assembly offer without actually having to go into the work field? Experience. As you create your project, as you deploy your code to that web development day next Monday, what you are doing is creating a portfolio of experience. Now when job hunters are recruiting you, you can say, oh, I actually built a Twitter API scraper. Boom. I actually built something that predicts Uber search pricing. Boom. I actually built a website that if you input pedal length and pedal width, it'll tell you to what degree of certainty what flower you're looking at. Boom. That sounds dumb to you now because you've been working with Iris for so long, but to someone who's never done this before, that's really cool. Oh, all I have to do is type in 4 numbers and it will predict what type of flower it is? That's kind of interesting. How do you do that? These are things that actually generate conversation in a topic about data science, okay? Most people who just come out of school don't have this. They can't do or understand any of this. As someone who's taught college, these kinds of classes are generally not available to undergrad. You have to at least get a master's in some kind of field to even look at a supervised machine learning model. This type of work is honestly graduate level work if you were to compare it to a university. Number 4, machine learning. So machine and learning were the number 1 and 2. The 4th most common phrase is the phrase machine learning. So obviously machine learning is a very important part of the data scientist's job, which is why machine learning is pretty much the number 1 focus of this class. Number 5, analytics, which is another fancier term, or just another term for data science. Team. The 6th most used word is the word team. Think back to your intro to data science lecture we had here. What, if you remember, what was one of the things that I mentioned about data science and those 3 domains? Statistics, computer science skills, and problem domain. What was one of the things I mentioned about those 3 in regards to a team?
People have these very different strengths.
Yeah, it was a while back, but essentially, more often than not, companies are more and more figuring out the fact that they're not finding people who are experts in all 3 of those things. Healthcare fields are having trouble finding someone who's A, knowledgeable about math, B, knowledgeable about computer science, and on top of those 2, knowledgeable about healthcare. They're just having a hard time finding that person. So what they're turning to are hiring teams of people. So you need to be okay with working in a team. Maybe you're the best machine learning specialist in the room, but you're amazing at data visualizations. You 2 now have to work together to make sure that your product works in harmony with each other, but it's exactly what the user needs. So teamwork is more and more important. Teamwork. Probably, I'm assuming teamwork. Statistical, obviously there is some level of math, and again, these words shouldn't be very surprising to you to see, oh yes, statistical is a very commonly used word in job description, but it is nice validation to see that these aren't me generating these words. These are job postings online, public job posting about data scientists who are posting these words. So hopefully this is some validation to what you've been doing in this class. Because there's no refunds. I gotta tell you that right now. I can't. Research, sure. Research is always a plus. Scientific, analysis, business is a big one. Project, techniques. Health is actually a very common word. Years is probably because I say 5+ years recommended of experience. Data mining, API usage, web scraping, data mining, that's a pretty big deal. Predictive, and then the next one is modeling. Predictive modeling is a very important part, which we all know is what? What is another word for predictive modeling? It's an S word. supervised machine learning. So we already said machine learning. Predictive modeling is just one part of machine learning. SQL. A lot of jobs are saying, work in SQL is preferred. Managed statistics, SAS. You don't know what SAS stands for? Software as a service. So a lot of these companies are turning to software as a service as opposed to a downloadable software. And then obviously software. And apparently knowledge is important these days. Who knew? But apparently they have to be very specific. Like, hey, knowledge, please have some when you show up. So they're making it very clear. You need to know SQL, modeling, and you need to have knowledge. Those are the three things you should take away from this. So I wouldn't call that silly, but I thought that was a really interesting thing to do because a lot of people ask me, what do I need to know going into a data scientist role? Is it machine learning? Is it SQL? Is it Python? Is it R? What do I need? And I can tell, we can talk about it all day, but here it is. This is what people want. This is what people are literally looking for on job descriptions. So I thought, again, this is in the fun folder, along with the Tinder and the Twitter API. This is your Indeed data mining tool. And you can change out the words. So instead of data scientist, you could do something like clown. I actually don't know what's going to happen if I do clown. I'm going to go through 10 pages of the word clown. 15 job descriptions. Fun day, painters, face painters, Apex fun run, children, operations personnel, fun bounce. So, yeah, you can change out with whatever job title you want and get some specific keywords on whatever job you're looking for after this class. It's fine. Some of them need to know how to juggle. That's cool. I can't juggle. All right. That was kind of funny, actually. Any questions on that? Feel free to play around with it. It should be fun. All right. Principal component analysis / dimension reduction. So I am looking at our slides first on class 17, dimension reduction. Some of you have been asking about dimension reduction, as you should be. Dimension reduction, again, is the final hole in the machine learning chasm that we've yet to cover in this class in depth. So after today, you will have seen the 4 biggest aspects of machine learning. To break it down, we'll talk about what dimension reduction is in general. We'll talk about 2 methods of dimension reduction. One of which is called principal components analysis, the other called singular value decomposition. For those of you who've taken a linear algebra course, these words actually probably seem familiar if you remember linear algebra. We will touch upon other methods if there's time, but if there's not, I'd rather skip over other methods and go right into the code, actually doing it in Python. So dimensionality reduction, and again, this is what I meant by the 4th quadrant. So pop quiz, everyone. So we got supervised, unsupervised, continuous, categorical. Can someone tell me what would happen? What is it called in the top left? Supervised, continuous. What is it called when a model is supervised and it predicts a continuous variable? What is it called? Regression. I'm glad I'm helping, guys. This is great. No refunds. Top right. You guys you're all whispering it to me. Like I can see your mouth saying the right word. Say it louder. What is it called when your model is supervised but categorical? That's one form of it. Classification. In general, a supervised categorical method is called classification, whereas continuous would be called regression. Logistic regression is a form of classification, as is KNN, as is decision trees. Linear regression is a form of regression, as is polynomial regression, as is, decision trees as well. What is it on the bottom right when we are doing an unsupervised model with a categorical, which is categorical in nature, we'll call it. Say it again. We did this already. We did this before today. When it's an unsupervised, but there's no response, but we're dealing with categories of some sort. Unsupervised categories. We don't know the categories. It's making up the categories, called clustering. And on the bottom left, we have the final piece of the puzzle, dimension reduction. Dimension reduction is generally thought of as the hardest of the four. Why? Well, people generally refer to unsupervised being harder than supervised in general. Because supervised, hey, at least you have something to aspire to. At least you have a response that you can say, well, at the end of the day, if I got the response, I'm on the right track. At least you can say that for supervised. We already know you can't say that for unsupervised. Does someone name me the metrics that we can use for clustering? What was the name of some of the metrics that we can use for clustering? To see if we're on the right track.
K.
So K means the type of clustering. What are the metrics to quantify how well we're doing?
Rock.
Say again?
Rock.
The ROC, the receiver operating characteristic, is actually a binary classification metric. Silhouette. Silhouette is one of them. Silhouette score is a way of combining two things. Does anyone remember what those two things are? Separation and cohesion. Separation and cohesion are two metrics that we can see how well if we're on the right track in unsupervised modeling. The silhouette score is a way of combining those two into one number. But again, there's no response. There's nothing to aspire to. These are just numbers that we humans put a meaning to. We humans. They'll never suspect. Dimension reduction is even harder. Because at least in clustering, I'm creating some kind of category. And then I can look at it and say, yeah, these make sense. In dimension reduction, I'm not even doing that. What is dimension reduction or dimensionality reduction? It's a set of techniques for reducing the size in terms of features, predictors, of the data set under examination. Essentially, how do I go from 200 features to 5 features and not lose anything? In general, the idea is to regard the data set as a matrix, which at this point is not weird to us because data sets, data frames, are row column structure. We regard it as a matrix, and then we decompose the matrix to a smaller, simpler, meaningful pieces. Which brings me back to dimensionality reduction is very much dependent on our features being continuous. Why? Because we are going to regard our data as nothing more than a matrix. Just a bunch of matrices it's a matrix of numbers. And again, if you've taken linear algebra, the point of dimension reduction is to take this matrix and to make it smaller, simpler, easier to work with. That, in terms of machine learning, reduces the number of features. There is a lot of math that goes into this. I will likely gloss over much of that math. However, I have included a 200-line piece of code in the code folder that goes through step by step all of the math, like literally done out without scikit-learn, if you want to see me do the math in code. But I will likely gloss over much of the nitty-gritty stuff, because I can already see you're bored. Why are we doing this? Because I like it when you're confused. No, I'm sorry, that's the wrong slide. The number of features in our data set can be difficult to manage. We're given troves of data, so much data. What is all of this? I don't know what I'm supposed to be looking for. Sometimes it's even misleading. Sometimes the relationships are a lot simpler than they appear. Hey, Samant, here's 100 columns. We think that if you combine them in some way, you're going to be able to predict, how much wine someone will buy at the store. That way we can better model our revenue for the upcoming fiscal year. Go for it. Well, hey, maybe let's just look at how many people come in the store today and on weekdays and weekends, and on average how much people buy. Maybe there's not much more to it than that. So oftentimes the amount of data we have is misleading, and dimension reduction can help us cut that down. For example, suppose we have a data set with some features that are related to each other. Like if I have one column that tells me how old I am, and the second column that tells me what year I was born in. Those seem related to each other. The point of dimension reduction is to find that relationship and to cut one of those columns out because they're not necessary. Maybe one of the columns is a linear combination of 4 other columns. If that's the case, I don't need that linear combination, I just need those 4 other raw columns. That's not obvious to us, but dimension reduction algorithms, it will be. We want to eliminate the redundancy as much as possible and consolidate the number of features that we're working with, or variables. If these relationships are linear combinations, then we can use very well-established techniques like we'll talk about today, including principal component analysis, PCA, or the singular value decomposition, SVD. Both of these techniques are ways of taking matrices and then boiling them down to multiplications of smaller matrices that are easier to work with. Here's the example that generally works the best for dimensionality reduction. Imagine you have a ball, a red ball, on a spring on a blue surface. And all that spring does is, oscillate back and forth. You pull on the ball and it goes back and forth, right? These blue things are cameras. They're cameras looking at this event in different dimensions. This camera is looking at it from the side. This camera is essentially getting a bird's eye view. This camera is kind of getting it from a slant. So look at camera A. All camera A really sees is this kind of motion back and forth. It's on its side. That's all it really sees. Camera B, which is looking pretty much top down, all it sees is going up and kind of going up and down like this. That's all it sees. Camera C, which is kind of at a weird angle, is like, yeah, but you're also kind of missing the fact that down here it kind of gets all wonky because it's away from its base and you're missing a lot of that detail. If you combine cameras A, B, and C together, you get a much better view of what's happening. Here's another example. What is this? It's not a trick question.
Chair.
It's a chair. What is it now?
Chair.
Still a chair. But if you look at it only from this view, what do you see? I see black panel with metal legs. I don't know what that is. For all I know, it's a really crappy plastic gravestone that you stick into the dirt. As soon as I do this, oh, it's a chair. I see that dimension now. I see the part where it goes this way. Dimension reduction is all about, okay, how many cameras do I have to put up to get the best view of the situation possible? Let me put it another way. Bless you. How many dimensions do we live in? 3. The answer is thank you. I was like, wait, I didn't need to open up like a debate. Let's assume there are 3 dimensions that we live in, okay? This chair exists in 3 dimensions, okay? Looking at the chair this way is 1 dimension. You are seeing this dimension of the chair. By looking at this alone, can you deduce with this degree of certainty that you are looking at a chair from only seeing this cross-section? Would you say yes or no?
Yes.
The second you say yes, you are admitting that you only need 1 dimension of data to predict whether or not this object is a chair. When you look at a photo on Facebook or Instagram, what are you actually looking at? You're looking at the 2-dimensional representation of what actually happened that day. As soon as you like that photo, you are essentially accepting the fact that you only need 2 dimensions of data to relive that moment with them. You don't need all 3. Humans are very, very okay with living with less dimensions than there are available to make the predictions that we need to do. We can already accept that fact. So cameras are my kind of go-to metaphor for dimensionality reduction. Now, how does it relate to data? Well, if I give you 100 columns, you could say I need 100 cameras to look at it. However, if you are willing to accept the fact that you can actually use less cameras, I can tell you, I'm going to set up 5 cameras. With those 5 cameras, you're going to be able to get as much detail as you would have gotten with those 100 cameras. And you're going to say, great, give me those 5 cameras. That's what we're going to be doing. That's what this is all about. How do we set up those 5 cameras in different locations to get the best view of what's happening. That's dimension reduction. The complexity that comes with a large number of features is due in part to the curse of dimensionality, which we have touched upon in this course. What it means is the sample size that we need to accurately estimate a random variable in d dimensions, so d, arbitrary number, grows exponentially with d. I.e., the number of data points that we need to accurately represent d is something like 2 to the d or 3 to the d. It grows exponentially. It's terrible. So if we only have 2 features, maybe we only need 10 data points. If you add a third feature, now we need like 100 data points to accurately capture that. You add a fourth dimension, now we need 1,000 points. You add a fifth dimension, now we need 100,000 points. The number of points we need to accurately represent the next level up in dimension grows exponentially. That's the curse of dimensionality. We need a lot more data when you add a new feature, in general. So if you have a great working model for predicting how much a car costs, and you're using the make of the car, the model of the car, the year of the car, and how used it is, how many accidents it's been in, you have a great model for how much that car costs. The second you say, all right, now I also want to add in, the zip code of where I'm buying it from. The second you add that next dimension, you, in general, need a lot more data in order to accurately represent that new added level of dimension. That's the curse of dimensionality. The point of dimension reduction is so that even when you add this new feature, can you place that camera in a different way so that you don't need more data? You can keep the amount of data you already have and still maintain your aspect of the data. Another way of saying this is that high-dimensional spaces are inherently sparse. And again, we've seen the word sparse before. It means that there's a lot of empty space. So if we have 2 dimensions, and we have some data points, content of this whole blob here, everyone's happy in the blob, right? Everyone's very happy in the blob. The second you add a third dimension, you just added infinite more space for that blob to take up. At a fourth dimension, you just added a literal infinite more amount of space for that blob to take up. You're just adding space with keeping the same number of data. So in order to keep that data condensed, you need to put more dots in there. That's the curse of dimensionality. With adding more space, you should add more data. A high-dimensional orange. That's a bad example. I don't know why I kept that. I'm sorry. That was a bad example. I'm reading through it now and it's bad. Okay. What's the goal? Is to analyze the data using the most meaningful basis or coordinates possible. This is a fancier way of saying, what are the best camera angles needed to look at the data? More precisely, given an n by d matrix, n rows and d columns, so essentially n observations and d dimensions of d features, d predictors, given an n by d matrix X, and I'll use our terminology X as our training set, or I'm sorry, as our predictors matrix, we want to find a k-dimensional representation, whereas k is less than d, at less than d dimensions, that captures the information in the original data according to the same criterion. So instead of having a 3 by 3, can I turn this into a 3 by 1 with only one column, but still maintain the same amount of data? Some of you are saying that's ludicrous. As soon as you remove those columns, you're just losing all that data. There's literally no way you can do that. Well, with the advent of linear algebra, there are actually ways of taking 9 numbers, turning it into 3, and then turning it back into 9 numbers without losing so much data. There are ways of doing this now. Can someone tell me when you think, obviously in machine learning it's nice to reduce the number of features. Can you think of another way that this can be useful? Can you think of something else that can be represented as a matrix? That would be nice if we could represent the same thing, but with fewer numbers. This is an open-ended question. What do you think? You smile because you have an answer? What do you think?
No.
What do you think?
Computer files.
Computer files. Does anyone ever wonder how compression works? Have you seen Silicon Valley? Middle lab doesn't exist, sorry. The middle lab algorithm does not exist. If you watch Silicon Valley, that makes sense. Well, it does exist in some sense, but it is not implemented. You're looking at me like it does exist. It does exist. There have been papers written about it, but it has not been implemented to its fullest extent. Compression is compression algorithms are a marketed version of this. How can we take computer files, images, videos, whatever, Excel CSVs, zip them up, and use less data to represent the same amount of data? Does anyone ever wonder, while you're compressing, it takes time, right? It's saying zipping, zipping, zipping. What it's doing is math. To compress this matrix into a bunch of smaller ones that are easier to hold. That's what reduces the file size. And then when you unzip it, all it's doing is taking these matrices, multiplying them together to get this big matrix again. So when you compress a file, it's taking the data, as represented by some kind of a matrix, splitting it up into a bunch of smaller matrices, which are just inherently less space on your computer. And then when you decompress it, it just multiplies them together again to get this big thing you started with. That's how file compression works. Which is why sometimes, and this is very, very rare, but sometimes when you uncompress a file, people have been known to lose data. Because sometimes when you compress files, this inherently will lose some of your original data. So the best compression algorithms lose as little data as possible while you do it. Which is why a lot of music professions don't like compressions. Because when you keep compressing files over and over again, the song inherently loses some of its, robustness. And as you do it over the decades, if you keep compressing the same file and decompressing it over and over and over again, you actually will start to hear differences in that audio file over the decades. Which is why lossless, that whole non-compression form, is very popular among musicians. Because they don't want to compress it because it loses actually part of its essence when you do that. And part of our lab today will be compressing an image file with Python PCA code. We'll be taking a file, making it to a quarter of its size, and it's still the same image. So the goal, in essence, to reduce the computational expense by taking a large matrix and turning it into smaller matrices, to reduce the susceptibility of overfitting, because generally as you add more columns, you add the chance of overfitting. Reduce the noise, again as you were mentioning, needle in the haystack, finding that needle in the noise. And enhancing our intuition, because 100 columns is hard to talk about, 5 is much easier. How? That's right, how, that's the point. Stop telling me why, and how. There are 2 approaches. Feature selection and feature extraction. You might have also heard the term feature engineering, which is a different term. Can someone tell me what is feature engineering? Sound it out. What are the 2 words? What is feature engineering? And can you give me an example of when you did it in this class? Feature engineering. Making new features. Yes. That is the definition of feature engineering, is making new features from old ones. Can you give me an example of when we did it in this class? What was it? Fair enough. So the stock data, as one example, we made a new column where we said, okay, did it go up or down, true or false? That was adding a new feature. Titanic, we did with the Titanic. We made the spouse column the spouse column, if they were at least 18 and they had at least one sibling spouse on board, that was feature engineering. You take that one step further, whenever someone has the word reverend in their name, add a column called religious figure, true or false. Sounds simple, but that is feature engineering. And Nick will actually talk about how we use feature engineering and selection and extraction to win that Kaggle competition. So that's actually part of this talk. So feature engineering is one of the ways we can make data better. Because better doesn't mean more or less. Better means narrowing down to the features that matter. Sometimes the features that matter don't exist yet. So that's engineering. But that's not reduction, right? Engineering is literally the opposite of reduction. That's adding features. So selection and extraction are the two types of reduction that we're going to be talking about. Selection is when we subset the features using an external criterion, such a filter, or some kind of a learning algorithm accuracy called a wrapper. So selection is literally saying, okay, I have three features in determining whether or not are the price of the car. The make, the model, and how many doors it has. Okay? Which of those three do you think is the least responsible for how much that car costs? The make, the model, and how many doors it has. Probably how many doors it has. I've had some very crappy cars with 2 doors. I've had some very nice cars with 4 doors. So you just selected 2 of the 3 features. That's it. Feature selection is literally just looking at your features and selecting which ones you want to do. I'll ask you a question. For regression, can someone name me a feature selection tool that we have used for regression? What is one way that we were able to pick out features in a regression problem?
Mapping the slope, mapping the slope.
We're on my track. Not the slope. Well, slope is one way we can see how much they're affected by, but there's another one that we did on that same day that told us, that literally was a number, a quantitative measure of how important that variable was in the regression. P-value. The p-value is one way that you can use in a regression to filter out your predictors. This is under debate. Yes, some p-values, some people say p-values aren't the best way to do it. I would agree. But p-values are a way of quantifying how important your variables are in a regression. How about for classification? Do you guys remember? Is there a way in classification? Yes, we can literally pick them out and then check our accuracy. Absolutely. But do you remember, it's actually very recent, there is a type of model that we can actually look at the importance of variables in a classification. What model is that? Decision trees. Do you remember what the name of that criterion was called? There's 2. Gini. The Gini. I know you meant. The Gini and entropy. Gini and entropy are 2 criterions for filtering out variables in a decision tree. So we've done feature selection before. I haven't always called it feature selection, but we've been doing feature selection since linear regression, which was day 3 or 4. We've been doing it for a while. Feature extraction is what we're going to be talking about today. Feature extraction is about mapping the features to a lower dimensional space. Taking a 3-dimensional image, all of us, and taking a photo, that's feature extraction. That's projecting 3 dimensions onto a 2-dimensional photo. That's not selection. I didn't just say, get rid of the z-axis. No, if you look at a photo, there's depth to it. Right? I mean, thanks Da Vinci for that, or around that time. We can now paint things with depth. So we don't just cut off the z dimension and look at x and y. Otherwise, that looks like, a Game Boy game. We can actually project 3D onto 2 dimensions. That's extraction. That's not selection. Selection would just be screw the z dimension. Just make it flat. Extraction would be, let's make it look like 3 dimensions using only 2. That's the camera stuff. So extraction is what we're going to be talking about. How do we map 100 dimensions into 5? Or later on, we'll be mapping 642 into 50. Feature selection is very, very important. But typically, when someone says the phrase dimension reduction, they generally mean feature extraction. So when someone says, I use a dimension reduction technique, they usually are referring to feature extraction. Again, you should ask to clarify, but usually they mean extraction. Because if they meant selection, they would say selection. I would say, I just disregarded number of car doors because it didn't make sense. That's not necessarily the hard part. The hard part is the extraction. So the goal of extraction, and this is the kind of overall concept here, is to create an entirely new set of coordinates that simplifies the representation of your system, of your data, of your model. Again, I keep going back to this model, this example, because it seems to work very well. It's about placing the cameras in the right way. It's about taking those cameras and then putting them in the right way to make sure that you're getting all aspects. It's like a security system in a building. There's literally an infinite number of ways you can look at a security system in a building, but you only have 20 cameras. How do you set them up in the most effective way possible? That's exactly what this is. How do we look at all of the building using only 20 cameras? So, here is one of the cameras of that box and spring. Here is, by the way, I included a link to the actual paper. It's literally called PCA, Principal Component Analysis.pdf. Here is one of the camera's data points from that box, or from that ball and spring. I think this is camera A. This is camera A. This is what it saw. So every couple of seconds, it kind of took a look down and then mapped, this is where the ball is, this is where the ball is, this is where the ball is. And this is what it got. Now, in a two-dimensional graph, here's X and here's Y, right? This is how we generally look at it. And this is where I'm going to challenge you all to think outside of the math that you've learned in the past. So before, when I asked you to try to visualize parallel coordinates, I asked you to kind of think outside the box of what visualizations mean. Here I'm going to ask you to think outside of the box on what a coordinate system looks like. We are very trained to think of dimensions as X, Y, and Z. That's how we've been trained to think as mathematicians. But those aren't always the best way of looking at something. Sure, your table has an X and a Y coordinate. Sure, the wood panels are arranged in perpendicular X and Y coordinates. But look at that data. It's slanted. Wouldn't it just be easier if you could just kind of tilt your head? Just kind of tilt your head, and you would say, oh yeah, if I tilt my head this way, then I can see the X and the Y, and it makes perfect sense to me. That tilting of the head is the feature extraction part. This makes sense when you look at if this were an axis, and if this were an axis, then this data is in perfect alignment with the axes. But if you look at it on X and Y, it's diagonal. So feature extraction is about how do I come up with these perpendicular lines to oppose our general interpretations of X and Y. That's a concept that's very new to most people. So I want to make sure that if there are any questions right now, I want to get them cleared up. The point of what we're going to be doing, what the math will be telling us, is it will tell us the directions of these lines. It will show us these axes and say, if you look at it from this perspective, the data makes more sense, as opposed to your traditional understanding of X and Y. That's the point of dimension reduction. Well, you might be asking yourself, well, Sinan, those are still two dimensions. All I did was tilt my head. Fine. What we're going to be doing is if this existed in 3 dimensions, we would still be looking for these perpendicular lines, but less than 3 of them. Okay, let's keep going, and then we'll see some code and some more graphs, and hopefully it'll start to make more sense. This is a brand new topic that I'm asking you to go along the journey with me. This will probably be our last super math-intensive class. I know, it's so sad. So what are some applications? Some of you mentioned file compression. I'll tell you some other ones. Topic modeling for document clustering. If I give you 10,000 articles How many, well, let me put it this way. I give you 1,400 job postings. And in 1,400 job postings, there are 28,000 through 1, 2, and 3 word phrases. Right? That's 20 times the number of articles and papers. What if I give you 10,000 job descriptions? You'd have hundreds of thousands of 3-word phrases. What if I want to look at 5-word phrases? We're getting into the millions of features. We're literally getting into millions of features. And yes, naive Bayes is a great model for dealing with many, many features. But in general, I don't want to deal with a million of these. I want to deal with 20 of these. So while I'm doing topic modeling, I want to think, can I just boil this down to saying, okay, statistics, statistical, math, analytical. Let me just say quantitative words. That's the new feature. Quantitative words. Instead of having a column for all these separate words, mathy words will go over here. And that's one example of doing dimension reduction in words. Image recognition and computer vision. Oh my God. Has anyone ever worked with MRIs before? MRI data? How big is an MRI image? It varies.
Yeah.
They did a PhD on MRI data.
Diffusion MRI things are like half big.
Your thesis, your thesis was on?
What?
Your thesis was on MRI images? Oh, I have no idea. How lucky I asked. Thank you. Half a gigabyte. A single diffusion MRI image can be half a gigabyte. I've seen pathology images or microscopy, like electron microscopy images, that when it was Dropbox to me, was a literal 20 gigabyte image. One image was 20 gigabytes. Because it was millions of pixels by millions of pixels. Because it was electron microscopes. The electrons were going in and looking at the images. Some of this data are humongous. And there's a startup in Baltimore, one of my good friends is running it, Proscia. Their whole business is about helping doctors deal with humongous pathology images. They have mathematicians on staff who do this to say, okay, you have a 20 gigabyte image, here, now it's only half a gig. And it's much easier to transport around and work with it even while it's only half a gig. That's a humongous, there's a huge opportunity there in image recognition and computer vision. Drones. Drones take 40 to 50 images every second. They're alive, quote unquote. They're alive, they take 50 images a second. To analyze all of those images, they have to be reduced very quickly so they can actually do topic modeling on them. Bioinformatics, gene expression. We have billions of genes. We have to reduce them into specific types. Speech recognition, astronomy. Again, there's a lot of stuff out there. And recommendation engines. Recommendation engines. When we're talking about Pandora or Netflix, content-based recommendations, in general, we have hundreds of thousands of different features that we use to predict. So we want to say, instead of these 100 features, can we boil them down to the 50 that matter? If one of our features is percentage of harp use in song, and no one seems to care about that, that's a way of dimension reduction saying, let's just not look at how much the harp is used in the song anymore. That's just a way of reducing the dimension of the data you have.
Do Siri and Dragon Speak really use?
I didn't hear what you said, I'm sorry.
Siri and Dragon Speak, do they use dimension reduction?
I'm sure they do. The question is Siri and Dragon Speech, right? That's what it's called? Is it voice recognition softwares? Do they use dimension reduction? Very likely. And the way they do it, probably, I've never worked for them. The way they probably do it is that the voice goes in and it's saved as a file, and then it's broken down into its principal components. And it says, okay, if these components exist, he's saying this word. If these components exist, he's saying that word.
So what would attribute?
What?
Oftentimes you use Siri and it doesn't give you the right words.
Yeah.
So what's the process there where you think you gave me this word, but actually you gave me the
That's more of like a marketing question that I don't know the answer to. Usually the answer is more data. The way they train these things, and I don't know if you've ever been contacted by Google for this, but there was a time for 2 years, Google would contact people in college, and they would say, hey, for free movie tickets, all you have to do is say these words into a microphone and then give them to us. What they were doing was just giving us free movie tickets, but we were training their speech recognition software. So they were learning, okay, here's 20,000 people saying the word bird. Now we're going to reduce them all into their smaller components, and then we'll notice that 98% of them have this component. Okay, this component now means bird. And that's how they can recognize, someone with a heavy accent and someone with a not so heavy accent, or a heavy accent in another language. They can now recognize both of them saying the word bird. Because they've broken the word bird down to its principal components. It's getting rid of the noise of accents and getting to the root of how does someone say the word bird? That's how they do the voice recognition. So if two people speak differently, that no longer matters because we're both saying the word bird and we can get to the core of what that means. Does that answer your question? Fantastic. My good friend Shakira here. This is one of my favorite examples of principal, have you guys seen this? A principal component analysis, and again, I put a link to it, and I have the code for it kind of remastered for our use. What I have in the data folder is a PNG called Shakira, and it is a photo of Shakira in black and white. A 642 by 450 pixel image of Shakira, if I'm not mistaken. What we're going to do later on, I'll show you, is that we're going to look at the same picture of Shakira using less components. So the image will start out by being 642 components because there's 642 columns of pixels. We're going to think of an image as nothing more than a series of numbers in a matrix. Because to a computer, that's all it is. An image is just a bunch of numbers in a matrix. And we're going to take that matrix, make it smaller, and then look at Shakira in a new light. So what we're looking at here, if we say, don't use any of them, this is what the image comes up with. It's just a blurred image, nothing. Then we use 10 principal components. 10, what does that number mean? 10 out of the possible 642. There are 642 possible cameras that were given to us. 642 cameras, we chose 10 of them, placed them in very good places, and we got something that looks like a human. Can you tell it's Shakira? No. Let's try 20 cameras, 30, 40, 50. With 50 out of 640, mind you, out of 640 potential cameras, using only 50, we can essentially reconstruct a near perfect image of a person. Which speaks wonders to many types of technologies, i.e., video-to-video conferencing. If we can use only 50 out of 1080, right, 1080 pixels, if we can only use 50 pixels to recreate 1080, that makes video conferencing that much faster and easier to do. There are softwares like Join.me, you might have already heard of it. Join.me takes advantage of that. It knows how to compress files very quickly and then share them so that video conferencing becomes much faster. And again, we'll see this in code. Principal component analysis, I want to start here and then we'll take a break. Principal component analysis is the first type of feature extraction model that we're going to look at. Principal component analysis is a dimension reduction technique that can be used on a matrix of any dimension. I make that a point because there are some methods that only work on square matrices, n by n. Principal component analysis is great because it works on any dimension. Like k-means being the most popular clustering algorithm, I would argue that principal component analysis is likely the most popular dimension reduction technique there is, followed closely by singular value decomposition. But PCA, excuse me. PCA is probably the most popular of the dimension reduction feature extraction techniques. The procedure will produce a new basis or a new coordinate system. Each of those components contains as much variance of the original data as possible. So it's trying very hard to recreate the data using less coordinates. Now, I'm not going to get into the nitty-gritty. Again, there is code that does this, but I don't want to get into it today. Because I get into a lot of math, and I apologize. But if you remember linear algebra, PCA of a matrix essentially boils down to the eigenvalue decomposition of the covariance of the matrix X. So essentially, you create from X, for any size data X, n by d, you construct the covariance matrix, which is essentially a variance of a matrix of relationships between variables, essentially. And then you take that matrix and you find the eigenvalue decomposition of it. For those of you who are curious, this is what it looks like. Given a matrix X, we will find the covariance matrix C. The covariance matrix, again, is a very large matrix, very sparse matrix. There's not a lot of data in the large matrix. Very sparse matrix where you get the relationships between different variables. It's like a scatter matrix almost. What we then do is we take this large matrix and then we break it down into smaller components, i.e. smaller matrices, which A, take up less space, and B, are easier to work with. Again, I'm going to not touch upon the math too hard, but I am going to mention it. It's done in the following way. The eigenvalue decomposition of C, that covariance matrix, is shown by multiplying three matrices together. Q, which is a matrix, times lambda, which if you remember from linear algebra is the Greek letter we generally use for eigenvalues, times the inverse of Q. So really it's only two matrices because one of them is the inverse of the other. We only need two matrices. The columns of Q are the eigenvectors of C, and the values in lambda, that's not the case lambda, the values of lambda in the diagonal are the eigenvalues of C. For those of you who don't remember or never learned what an eigenvalue is, this is what it is. This is how this works. If you have a matrix C, and a matrix, again, is like a 3 by 3 or a 4 by 2 or some matrix. But if I have a square matrix C, an eigenvalue and vector are a vector and number such that the following is true. If I take C, the matrix, and I multiply it by a vector V, and how do you multiply matrices and vectors? Well, that's like saying, well, if I have this 3 by 3, and I want to multiply it by 1 to 1, I literally have to go 0 times 1 is 1, 0 times 1 is 0, plus 1 times 2 is 2, plus 2.2 times 1 is 2.2, so the first value is going to be 4.2. You have to do all of the dot products and all, you must likely coming back to you are already falling asleep. But the point is, if you have eigenvalues and vectors, if you multiply these, it's the actual same thing you would get is if you multiply that same vector by a single number called lambda, or it's an eigenvalue. Essentially, we are reducing matrix multiplication into multiplication by a single number. It's a way of saving time and computation cycles by multiplying by less things. And this is what makes PCA possible. This is what allows us to take a 3 by 3 and represent it as a 3 by 1 and not lose that much data. And I have resources on eigenvalues and eigenvectors if you want to brush up on your linear algebra as well. So why do we do this? Well, math is beautiful. And what ends up happening is that those eigenvectors, these v's, there are many of them, they actually form a perpendicular coordinate system that cradles your data in a different way than x, y, and z would have. These eigenvectors actually form your new coordinate system that work better than x, y, and z. Oh, I'm sorry. And they're orthogonal. Does anyone know what orthogonal means? It's a fancy word for a word I bet you all know. Perpendicular. Orthogonal is just another word for perpendicular. Yeah, I know. We like to make up words. Sound fancy about it. Is there something you'd like to share with the class? I'm sorry.
I was just checking the half of lambda was a diagonal matrix.
It is. It is, for those of you who are curious.
That's it. That's my secret.
For those of you who are curious, Q is a square matrix because it has an inverse. Lambda is a diagonal matrix, which means it only has values in the diagonal, everything else is 0. Those diagonals are all eigenvalues. Q has the eigenvectors, that forms the basis, the coordinate system. Furthermore, well, where does the principal component part come into all of this? Let's see. The principal component part comes in if you list the eigenvalues from largest to smallest. You can call those eigenvalues your principal components. The largest eigenvalue corresponds to the most important coordinate, or axis, I'm sorry. The largest eigenvalue corresponds to the most important axis. Each axis comes with it the amount of the variance of the data that it explains. What that means is, if I have a two-dimensional data that looks like this, so you can see I'm kind of going in a diagonal. There is another dimension to this. There's a diagonal, but there's also, it goes this way, and it also goes a little bit this way. The larger principal component would tell me that this is the most important axis. Is that your data is not a blob, it's actually more spread out in this direction. Sure, yes, and it's also represented by going a little bit this way. But for the most part, it's spread out in this direction. The variance is best explained by looking in this direction. So the larger principal component will tell us this is the way it's pointing to the most. And we're going to recreate this plot in Python, but there's a way of showing us how many principal components we actually need. Okay, let's take a break. Let's take a break. Let's take a 15, 20-minute break. Let's come back around 8:05. We'll keep on going. My goal is to be done by 9 so that we can have half an hour of project work for questioning with us. Which begs the question, do I have time to see the value decomposition?